So we'll continue from where we stopped. Today we'll be talking about ECG graphs. So this is how the ECG graph looks like. It has small boxes and it has big boxes. These thick lines that you can see on your screen represent the big box, while you can see some faint thin lines in it represent the small box, just like how every graph book looks like. Now, in a big box, there should be 5 small boxes. So let's count. This is the horizontal plane and this is the vertical plane. So 5 each. 1, 2, 3, 4, 5. Those are the 5 small boxes on the horizontal line and 5 on the vertical line. Now, the horizontal line serves as x-axis in your physics and the vertical line serves as y-axis. The horizontal line represents duration and the SI unit for that is seconds. In some textbook, they will say milliseconds. Now it's different. Seconds. Let's use seconds for this lecture. In terms of the vertical line, amplitude, right? We use millivolts as the SI unit. Millivolts. Definitely, 1 millimeter is the duration of a small box. A small box is 1 millimeter, while a big box is 5 millimeter. In duration, the machine has been calibrated to run 25 millimeter per second. So you listen at this point, 25 millimeter per second. So if I count 25 small boxes like this, that's like 5 big boxes. What I'm saying is that this duration from here to about this place to this end is 1 second. So what is the value of one small box? If 25 is 1 second, that means you say 1 divided by 25, and that will give us 0.04 seconds. Look at it here, 0.04 seconds. Now, what that means is that 5 of that will give you 0.2 seconds. The value of a big box and duration is 0.2 seconds, while the value of a small box on duration is 0.04 seconds. Let me come again. The machine has been calibrated to run 25 millimeter per second. So 1 millimeter is 0.04 seconds. Definitely 25 of that will give you 1 second. As simple as that. Now the machine has been calibrated to run 10 millimeter per seconds, per millivolts, sorry. 10 millimeter per millivolts. What that means is that if I should count 10 small boxes from here now, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's 10. So 2 big boxes is equal to 1 millivolts. That's what I'm saying. 10 millimeter equals 1 millivolt. So what's the value of one small box? What I just need to do is just 1 divided by 10, and that will be 0.1 millivolts. That's what you have here. So a small box is 0.1 millivolts, while a big box will be times 5 of that, because 5 small boxes makes up a big box, and that's what you are going to have, 0.5 millivolts. Let me just put you straight. So in a nutshell, what I'm saying is that if a small box on the x-axis is 0.04 seconds, definitely 2 small boxes on x-axis, that is in duration, will be 0.08 seconds. Okay, a small box on the y-axis amplitude is 0.1. 3 small boxes will be 0.3. With this explanation, you should be able to understand this now. Don't get it confused. People cram this, but that's how it's being gotten. Just write it down, do your marks. If 25 millimeter equals 1 second, what is the value of 1 millimeter, which is a small box? If 10 millimeter equals to 1 millivolts on the y-axis, what is the value of 1 millimeter if 10 of it equals 1 millivolts? You will realize that you are going to arrive at this. There's no magic there. Alright, so we're going to the next topic now. Now, in the previous lecture, we were able to identify these waveforms for us. We're able to show you what a P wave is, what a KRS complex is, what a T wave is, and all the likes, even the segments and the intervals. If you are not familiar with this, you can look up at the first lecture. You are going to see that. So now we are going to be talking about this waveform one after the other. Let's take P wave first. Looking at P wave, there are about 5 criteria that makes a P wave normal. This is a P wave. Now this is a P wave. This is a P wave. P wave is the first positive waveform that you see before a KRS complex normally. The first thing is P wave should be present. You don't have any business, you know, knowing if a P wave is normal or abnormal when it's absent. There are conditions that the P wave might be absent. Example, atrial fibrillation. It's absent. In some cases, it might be replaced by fibrillatory waves. Those things are not P wave. Atrial flutter. P wave is absent. What you see is what we call flutter wave, which is sawtooth wave. When we get to cardiac rhythm, we'll show you examples of these waveforms. Now, it could be absent also in junctional rhythm. In this situation, you might see an inverted P wave in junctional rhythm, or you might not see a P wave at all. Thus, the first criteria is P wave should be present. The best waveform you can use to identify P wave, the best lead is lead 2, because that's where you have the most prominent P wave. Now, P wave, aside from being present, which is number 1, it should be positive. Positive means that it should be upright. Just like this now is going up, is not coming down. A negative deflation is coming down. Now in EEG, when it's going downward is positive, when it's going upward is negative. But in terms of ECG, when it's going upward is positive, when it's coming downward is negative. So a P wave should be positive. Now, when you have a P wave that is negative, what does it mean? Like you have an inverted P wave. That could mean a junctional rhythm, an atrial rhythm, or it could mean those two major things and some other meaning, but it is not a normal P wave. The moment it is inverted, it is normal. The moment it is absent, it is not normal. Now the third thing is that a P wave should be single. Single means it shouldn't be 2, it shouldn't be 3, it should just be 1. Now, there are some abnormal cases whereby you see multiple P wave. Single, but in atrial fibrillation, what you see is plenty P wave-like waveforms. Those things are not P wave because a P wave is meant to be single. So what you have is a fibrillatory wave, that is atrial fibrillation, and flutter wave as well. You see sawtooth waveforms. When we get to rhythm, you see all these things. So a P wave should be single. The next thing is a P wave should be uniform. What I mean by uniform means that it should have the same shape. When you have this in the first rhythm, the next circle should have the same thing. The next circle should have the same thing. But if you have multiform, it's abnormal. You see a shape here, see another shape, maybe small here, it's now suddenly big in the normal this thing. The next rhythm that is big, it could be premature atrial complex, whereby P wave fills into T wave and make a giant P wave. That's not a normal P wave at that end. Now, in some rhythms whereby you can have a P wave that has different shape, there's a rhythm called wandering atrial pacemaker. In this situation, the atrium, is depolarizing the heart, is the pacemaker, the head signal is the pacemaker, everything. So they say wandering atrial pacemaker. You don't know what is the pacemaker. So in this rhythm, you have multiple shape of P wave. Now, the last thing, I've mentioned one. I said it should be present, positive. I said it should be single, and it should be uniform. It should be the same. Now, the next thing is that it should be round. It should be round in shape. It should be round. That is like semicircle, just like this. It should be somehow round like this. Now, those are the major morphology of the P wave. How the P wave should be present, positive, uniform. Then it should be single, and it should be round. Those are the five things. The other things that you look at in a P wave is in terms of duration and amplitude. When a P wave, the normal duration of a P wave is 2.5 small boxes. We just finished the graph. So when I say 2.5 small boxes on duration, what I'm saying is that 0.4 times 2.5, definitely. So it's just like 0.10, 0.04 rather, sorry, 0.04, in 2.5 places. That's 2.5 small boxes. That's 0.10. If your P wave is more than 0.10, probably maybe 0.12, that's about 3. It's more than 2.5. You say it's a wide P wave. And what that indicates could be left atrial enlargement. Left atrial enlargement, which is also called P mitral. You can see an example here on the screen. If you count the small boxes here now, it's up to like 5, thereabout. It's more than 2.5 small boxes. So you say the P wave is what is wide, and that is left atrial enlargement or P mitral. Now, when your P wave is tall, more than 2.5 small boxes, when your P wave is more than 2.5 boxes, you'll be thinking of P pulmonale, which is right atrial enlargement. So you'll be thinking of right atrial enlargement when your P wave is more than 2.5 small boxes tall. You'll be thinking of right atrial enlargement. That is the morphology. Now, P wave most times are upright in all leads. In lead 1, lead 2, lead 3, ABR, sometimes inverted in ABR is still normal, it will be upright, ABL, ABF, but P wave normally is biphasic. What I mean by biphasic, let me draw it for you. Now, this is P wave that is upright, right? Now, biphasic means it's going to be like this. Look at the screen. Now, when your P wave is biphasic like this, you see that in lead V1. So in lead V1, the P wave is normally biphasic like this. Now, in this condition that I said the P wave in is taller than 2.5 small boxes, you think right atrial enlargement, abi, RAE, RAE. Now, what again you see in V1? This is in lead 2. What you see in V1 is that this first part is actually the right atrium. The second part is the left atrium, which means that when the SA node is depolarizing, it's located at the right atrium. So the right atrium first depolarizes first. So in right atrial enlargement, this will be taller. It will be like 2 times of this. Now in left atrial enlargement, definitely this will be longer. You can use that to also predict, but the best one is to just know if it's wide or if it's tall. But you can use this. That's one of the significance of this. Now that is that about the P wave morphology, the duration, and also in all the leads, in the 12 lead, how it presents itself. Let's go to the next waveform. Okay, let's talk about this. This is what I was explaining in lead 2. You can see it's upright. Then in V1, it is biphasic. You can see it. In right atrial enlargement, it is taller than 2.5 small boxes. So if you should look at this will be taller than 2.5 small boxes. So this is right atrial enlargement. So in that situation, you can see that it's taller here. Then in left atrial enlargement, if you count the small boxes here in a P wave, you can see that it is more than 2.5 small boxes. So, and you can see that the second part is longer than the first part. So now you can have biatrial enlargement whereby it is tall, you know, it is tall, and also it is wide as well. So in this situation, you have it also in your V1. Thank you very much for this P wave lecture. Let's go to the KRS complex. The KRS complex is a complex because it's actually 3 waveforms that forms the KRS complex. 3 waveforms. The waveform includes the Q, the R, the X. Now the reason why we call it a complex is that 3 of them represent ventricular depolarization. Although one represents the early part of the depolarization, the middle part, the late part, and how electrophysiologists can prove that. But definitely If any of this waveform in isolation is present, then everything is present. For example, if the Q wave, the R wave is the only one that is present, you can see there's no Q wave here. QRS complex is present. If the look at the screen, please. If the R is present and the S is present, the R is longer than the S, the Q wave is not there, it is still a QRS complex. If the R is now smaller here, but S wave is the one that is longer, but there's no Q wave, it's still present. Now, when you have this Q, you have the R, and you have the S. This is the S down here. This is the Q. Q and S, they are negative deflection. It's only the R that is positive. You can see it here. It's still a QRS complex. If there is Q, this is a Q. Q comes before R, then S comes after Q. So you have Q here, you have R here. It's still a QRS complex. Now, this is actually funny though. Well, you have a Q and you have a S, there is no R. It's still a QRS complex. If you have a Q that is deep and you have a R that is small, it's still a QRS complex. Now, this particular pattern, which we call RS prime, is called M-shaped QRS complex as well, where you have an initial small r, then S already. Then you now have a giant R suddenly. So we call it R prime. That means you're having two R. In this situation, we call it M-shaped QRS complex, and it could actually indicate bundle branch block. So if it's right bundle branch block, you have this pattern in your V1 and V2. When it's left bundle branch block, you have it in V5, V6. Okay, you can quickly write that down. Similar to everything I've explained, you can see a Q and R and there's no S. So all these patterns are valid. This is various patterns that you QRS complex can present. This is simple. When your president is going out, it can't go out again. It can send a representative, which is a vice or maybe a deputy or someone to represent him. So the moment any of the waveform is being represented, the QRS complex is being represented. Sorry, the moment any of the waveform is being present, the QRS complex is being represented. But in absent QRS complex, you will not even see any of the waveforms. Now, a QRS complex is regarded wide or narrow based on duration. If the QRS complex is less than 3 small boxes, that is 0.12, you call it narrow QRS complex. If it's wider than 0.12, that is wider than 3 small boxes, it's different from P wave. P wave is 2.5, but QRS complex is 3 small boxes. That's why we taught you about the ECG graph. Now, if it's more than 3 small, just like this, now look at 1, 2, 3, and it's even up to 3. The moment it's up to 3 or greater than 3, is wide QRS complex or broad QRS complex. Now, why do you call it? What is the risk when you have a wide QRS complex? I know some nurses will be smiling now. The first thing that comes to your mind is VTAC. When you have a QRS complex that is wide and there's an absent or retrograde P wave, you'll be thinking of VTAC. Now, when you have a wide QRS complex, another condition that can make a QRS complex to be wide is actually ventricular conduction delay, intraventricular conduction delay. This can make your QRS complex wide. Even bundle branch block can make your QRS complex wide. Another thing that can make your QRS complex wide is also premature ventricular complex. You just suddenly see a wide giant Q wave QRS complex that will just appear. It should be wide. Those conditions are differentials for wide QRS complex. So a QRS complex can be narrow and a QRS complex can be wide. Another pathology of the QRS complex is that a QRS complex is meant to be a Q wave, Q wave is meant to be less than 1 small box, even if it appears. The lead it appears most. Some people will say inferior lead, some people will say lateral lead. In the first class, we explained lateral lead, which is lead 1, AVL, V5, and V6. They give information about the lateral wall of the heart. So inferior wall leads are lead 2, lead 3, and AVF. So in this situation now, you can see a QRS complex, a Q wave rather. This is a Q wave before the R wave. You can see it here, but they still regard this as normal because it's not greater than half of. When your Q wave is greater than half of the Q in the R wave, sorry. When your Q wave is greater than half of the R wave, is regarded as pathologic, or if it's more than 1 millimeter or 2 millimeters. But in this situation now, you can see it's not even up to half of this. This one is not up to half of this. So you say, okay, maybe it's still a normal Q wave. But in this situation, you can see it's even more than half of this. See your Q wave here for your R wave. It's more than half of this. You say this is a pathologic Q wave. Now, Q wave can indicate old infarct. It could also indicate a patient about to have infarction. So most times we look at the Q wave more in inferior leads to actually know if it's pathologic or normal. One amazing thing about the Q wave also is when we talk about the voltage of the KRS complex. Sorry, one amazing thing of the KRS complex is when we talk about the voltage of the KRS complex. The voltage of the KRS complex could be higher than normal and also can be lesser than normal. Voltage is the same thing as amplitude, millivolts. So voltage means vertical, how tall it is. Now, when do you say you're having a low voltage KRS complex? You say you have a low voltage KRS complex when the KRS complex is actually lesser than 5 millimeter. That's a big box on the limb leads. Limb lead is lead 1, lead 2, lead 3. This is a rhythm strip. This lead 2 here is the same lead 2 here, but it's elongated. Now this lead 1, lead 2, lead 3, AVR, AVL, and AVF. These are limb leads. Although this is a bipolar lead, these are unipolar lead or augmented lead. Now, V1 to V6, all these leads that you are seeing, this is where the leads are separated. You can see this mark here. So I'm saying from here to here is AVR. From this line now that you are seeing to this end is your V1. So from this line to this line is your V4. This is the calibration sign. If you don't see this sign, don't interpret the ECG. So this is show that standardization means that the ECG has been calibrated to run in a particular minute. And look under the ECGs that you are reporting. When you say 25 millimeter per second, you go on with this all these teachings I'm teaching. But if you see 50 millimeter per second, then you make some adjustments in your calculation. So it's not going to be 0.04 seconds anymore because now 50 millimeter equals 1 second. So you just figure those mathematics, use the formula. That's why in the beginning I taught you how they calculated that. First thing, if it's less than 5 small boxes on the limb leads, it's regarded to as low. Then you look at the chest lead. If it's less than 10 millimeter, because the chest lead used to have higher voltage of KRS complex, so definitely we give it 10. So if it's less than 10 here and it's less than 5 here, you regard it as a low voltage KRS complex. What are the conditions whereby you can have a low voltage KRS complex? The first one is obesity. When a patient is obese, big, so anything that can impede conduction of impulse, because ECG picks up conduction, electrical activities of the heart. So anything that impede that, towards the body surface, because you have to place those electrodes on the body surface. So things like obesity, things like emphysema, air in the lung, trapped in the air that was trapped in the lung. Another thing is pericardial effusion, pleural effusion, and so many other things. So when you see this low KRS complex, you'll be thinking, and also heart failure. Most times diastolic heart failure, DCM. Also, if a patient has what we call amyloidosis, it could have low voltage KRS complex. A KRS complex is not also meant to be higher than its particular range. So if a KRS complex is more than 20 millimeter on the limb lead, you just see your ECG waveform. You see that KRS complex, maybe the R wave, for example, is longer than 20 small boxes. We're suspecting left ventricular hypertrophy. So we have different criteria for left ventricular hypertrophy. We have the most common one, Sokolo-Lyon. This is being calculated by calculating the number of small boxes in your V1. That is the S wave in V1. S wave is the one after the R wave. So when you count the number of small boxes there, just like a story building, ground floor, first floor, those like that. So you count the small boxes to know like if it's as long. Let me just draw something for you to see. So my pencil. So if it's like this now, you just start counting one, the small boxes, continue to count, blah blah blah. So you count it to the end here, where it ends. So you know the number of small boxes there. Then you count this number of small boxes in either V1 or V6, V5 or V6, the R wave there. So you continue to count upward, like count that one upward like this, okay, to the apex of that R wave. So when you count, let's say you count 20 here, you counted 20 here, and you counted 15 here. So anything that makes the summation of this to be up to 35, hmm, or greater than 35, you say there's LVH. So this is a voltage criteria for LVH. Now, this is not a very strong criteria for LVH because there are people that have higher voltage, like children and all that, they have higher voltage. So it's more like significant when you are having greater than 40, when you calculate it and it's giving you greater than 45, for example, then you know there is an LVH. Because at times when you get 36, the patient on echo might not have LVH. So there's one that is more specific for LVH compared to both of them, which is the cornell. So cornell is more specific. But in terms of cornell voltage criteria, you use S wave in V3, S wave in V3 instead of S wave in V1. You use S wave in V3, then R wave in AVL, not V5 and V6. So you use that. Then if your value is greater than 28 in men, there's likely going to be LVH. Now, if it's greater than 20 in female, there's likely going to be LVH. This was worked upon by um, Murphy. Murphy worked on this and said, okay, instead of using SV1, you can use either SV1 or SV2. So someone also modified this cornell voltage. So they call it modified. So they call it modified cornell criteria, which is the strongest now. All you just need to do in modified cornell criteria is to look at AVL if it's greater than 11. If the R wave in AVL is greater than 7 or 11, then you say the patient has LVH. Okay, so that's that about left ventricular hypertrophy. Let's do an example of LVH here. You can see from here, let's use Sokololion for example. This is 1, 2, two small boxes. Then this is 5 small boxes. Under 5 small boxes, that's 12. Then under small boxes, that's 17. Under small boxes here, that's 22. Okay, 17, 22. This is 22 already. Now let's use V5. Two small boxes here as well. If you should count, you will see it. Two small boxes, 5, 7, 12, 15. Let's just give it 16, or yeah, 16. You can see it here. 16, one small box. Now that is 22 plus 16. That's 38, right? 22 plus 16. That's 38, right? So 38 is greater than, sorry, let me write it. So it says it's greater than what? It's greater than 35. Good. So that is LVH based on Sokololion voltage criteria. Now you can see the S wave here. Now let me quickly use the opportunity to explain this chest lead. Normally, there's something we call R wave progression. R wave progression means R wave here will be small, this will be longer, this will be longer. Then it somersaults when it gets here. You can see a longer R wave, R wave. So that's an R wave progression. In V3, V4, it's meant to be biphasic. The KRS complex is meant to be biphasic, but in most cases, it's always negative here and it's positive in V4. That's that about the. So let me use the opportunity to also talk about the morphology of the KRS complex. Morphology, how it's supposed to present in most lead. I'll talk about the duration, I'm talking about the amplitude. I'll still talk about the right ventricular hypertrophy. But one important thing as well that you should know about the KRS complex is that it should be positive in lead 1. Positive means to be upright like this, like what you have in V5 here. This is a negative KRS complex. So it should be positive in lead 1, lead 2, lead 3, AVL, AVF, V5, V6, and most times V4. Positive, upright like this. Should be upright like this. Now, negative means it should be like this. S wave should be longer than the R wave. So it should be negative in AVR, V1, V2, and sometimes V3. So biphasic, it could be biphasic in V3 and V4 because those are the transitional points where the R wave progression somersaults. If someone starts slowly, it increases in V2, get bigger in V3, then V4, V5 get bigger, bigger like that. So if you have poor R wave progression, it could mean LVH, it could mean heart failure, it could mean so many things. Now, that's that about that. Let's quickly go to the next thing because of time. This is another LVH now. You can see in AVL here. This is about 3 small boxes, 8 small boxes plus this. That's 13. That's greater than 11. So modified voltage criteria shows that this is LVH. Modified Cornell voltage criteria shows that this is LVH. Now you can see here there's an abnormality also of the KRS complex. It's negative here. It's meant to be positive in the 2. It's not negative. It's negative here, negative here. So this is what we call left axis deviation. So we'll get to that soon because it's meant to be positive here. It's meant to be positive here. These are inferior leads, lead 2, lead 3 area. But it's actually, instead of it to be positive, it's not negative. So that's the left axis deviation. Left axis deviation. Now for right ventricular hypertrophy, the major thing we look at for is in V1. When the R wave is greater than 7, the count is greater and there's no body branch block. Those are times when it's positive like this. It's meant to be negative in V1, KRS complex, if you remember. But if it's positive like this and it's more than 7 and there's no body branch block, you look at the right axis deviation also. You'll see a right axis deviation in the limb leads. So you see that this is actually, or some people say R ratio S if it's greater than 1 when you do the ratio of both of them. So in this situation, you can see there's right ventricular hypertrophy. There are other things they look at for, but that's the major voltage criteria for right ventricular hypertrophy. Now the KRS axis. So this is what we call a Zazier system, which you divide this into four equal. So this will be 0 degree. From here to here is 90 degree. Remember your physics, your mathematics. 90 degree, all this isosceles triangle, blah blah blah, obtuse triangle, all this. So you can know that this is 90 degree angle on a straight line. Now, from here, from this 0 to this point is 180 definitely. So this is more like you're going negative, you are going positive, this clockwise, and this you are going negative anti-clockwise. Now you now label it. Let's take this for lead 1. This is lead 2 at 60 at 90 AVF. This is lead 3 at 120. Then AVR at minus 150. So from minus 30 to plus 90, that is a normal KRS axis. This part might be complicated. You follow me gradually. Now from minus 30 to minus 90, that is left axis deviation. From minus 90 to about 180, so about 180, that is extreme axis. Now from 180, that is plus 90 to 180, that is right axis deviation. How do you now calculate this? All you just need to do is that if you have a biphasic KRS complex in any lead or any lead in the limb lead that has a very small voltage of KRS complex, you pick that lead. So if that lead is, let's say in lead 1, I have a biphasic in lead 1, so I'll be here. Let's say I have a biphasic in AVF, I'll be here. Now if it's a perfect biphasic, it means I'm going 90 degree. If my lead 1 is positive, I'll be going towards lead 1. If my lead 1 is negative, I'll be going like this. So let's take for example, if I have my biphasic in ABF and is a perfect biphasic in ABF, and my lead 1 is negative. My lead 1 is negative, not positive. So I'll go this way. That's 180, and that's right axis division. That's right axis division. So if let me now show you an example to explain this. If it's not perfect biphasic, for example, R is R minus S plus. R minus means if the R wave is longer than the S with one box, in that your biphasic is longer. Biphasic means you have R, you have S. If R wave is longer than S by one small box, you say plus 10 and minus 10 because R minus. Now 90-degree is what you are supposed to travel. You will now be traveling 80-degree. So you stop at like 170 here. But if it's more than two small boxes, you use 20. So you'll be stopping at 160 because you say 90 minus 20, and that will give you 70. But if it's S wave that is longer, vice versa, you add 10 to it. So if S wave is longer, I'll add 10 to it with one small box. But if it's two small boxes, I'll add 20. So instead of 90, I'll be saying 100 or 110. Let's quickly show an example. Now, there's a shortcut to this axis. Shortcut. The shortcut means that you just look at in lead 1, is lead 1 positive? Positive means the KRS complex is upright like this. Negative means it is like this. Now let me quickly explain this. This positive deflection means that the current is going towards the electrode. Now if the current is going away from the electrode, it will be negative like this. The current coming from the earth. Now when the current coming from is at 90-degree, it will be biphasic. So normally KRS complex is meant to be positive in lead 1 and positive. Don't use AVF. Sorry about this. Don't use AVF. AVF is an old method. The reason is that you can see the normal here. Normal here, they use 0 to 90. But in the previous class, I show you minus 30. Minus 30 to 90. So they don't use AVF anymore. Now we use lead 2. So change this to lead 2. Lead 2. Please change this to lead 2. Now this lead 2, when KRS complex is positive in lead 1, upright like this. So when KRS complex is positive in lead 1 and positive in lead 2, you say it's a normal KRS axis. When it is positive in lead 1 but negative in lead 2, you say it is what? Possible LED, left axis division. When it is now negative in lead 1, negative means like this, and it's positive in lead 2, you say it's right axis division. When it's negative in both, you say it's extreme axis division. So these are ways that you can use to classify a KRS complex axis. Now let me give you an example of what I'm trying to explain. Looking at this now, this is a left axis division. It is positive here but negative in lead 2. Okay? Now, if it's negative in lead 2, you see it also in other leads. But lead 2 is one of the strongest inferior.